The architecture of modern civilization rests on an invisible, omnipresent foundation, the science of measurement. Metrology, the rigorous study and application of measurement standards, is the silent language that allows global trade to function, medical science to save lives, and aerospace engineering to conquer the stars. Yet, for the vast majority of human history, this language was a fragmented, chaotic dialect. The journey of metrology from a localized subjective practice to a universal quantum-based system is one of the most profound intellectual triumphs of the human species. This evolution reflects a fundamental shift in how humanity relates to the physical universe, transitioning from a reliance on terrestrial artifacts to an embrace of the immutable constants that govern the cosmos. Before the dawn of the 18th century, the concept of a standardized universal system of measurement was virtually non-existent. Across the globe, measurement systems were a bewildering patchwork of inconsistency, largely based on agricultural yields, local feudal decrees, or the arbitrary dimensions of human anatomy. In pre-revolutionary France, this lack of standardization had reached a point of absolute crisis. It's estimated that a staggering 250,000 distinct units of weights and measures were in active use across the country. The practical implications of this chaos were severely detrimental to society. A merchant traveling across a single region would find that the local unit of length, the foot, varied wildly. Depending entirely on the specific town and the influence of local trade guilds, the foot could range from roughly 27 centimeters to 34 centimeters. Volume was equally unpredictable. A pint of liquid in the heart of Paris was significantly larger than a pint measured in the neighboring district of Saint-Denis. In certain regions, land area was not measured by geometric dimensions, but by how far a man's voice could carry across a field. This bizarre fragmentation created tangible, daily harm. It allowed for arbitrary and unjust tax collection, made scientific results impossible to reproduce across national borders, and severely hampered economic trade by necessitating a massive network of local intermediaries whose sole job was to translate regional units for traveling merchants. The intellectual seeds for a rational alternative had been planted earlier. In the year 1668, an English clergyman and natural philosopher named John Wilkins proposed a coordinated decimal system of units for length, area, volume, and mass. Wilkins envisioned a universal measure based on the length of a pendulum that had a half-beat of exactly 1 second. 2 years later, a French vicar named Gabriel Mouton proposed a unit of length based on 1 minute of arc of a great circle of the Earth. However, the political climate of the 17th century was not yet ready for such sweeping reforms. It was the French Revolution that finally provided the political upheaval necessary to shatter the old systems. The revolutionaries sought to rebuild society on a foundation of pure reason, abolishing the last vestiges of feudalism, including the right of local nobility to control weights and measures in their fiefdoms. In 1790, the French National Assembly commissioned the Academy of Sciences to create a universal measurement system. The guiding philosophical principle of this endeavor, championed by intellectuals like the Marquis de Condorcet, was that the new units must be based on nature itself. Condorcet, who tragically took his own life during the Reign of Terror to avoid the guillotine, deeply believed that a universal system would allow all people to calculate their own best interests, a prerequisite for genuine equality and freedom. He famously declared that the measurement of the eternal spherical Earth would be a standard for all people for all time. To enact this vision, the Academy defined the foundational unit of length, the meter, exactly 1/10,000,000th of the distance from the North Pole to the equator measured along the meridian arc passing directly through Paris. Simultaneously, the unit of mass, the kilogram, was defined as the mass of 1 cubic decimeter of pure water at the temperature of its maximum density. To anchor the meter to reality, astronomers Jean-Baptiste Joseph D'Alembert and Pierre Méchain embarked on an incredibly arduous 6-year survey to measure the meridian arc from Dunkirk to Barcelona amidst the chaos of the Revolution.
Although Mechain realized he had made a slight error in measuring the latitude of Barcelona, an error he kept secret out of profound professional anxiety, the survey's data was ultimately used to forge the physical standards. In June of 1799, the new system was codified into law with the creation of the Metre des Archives and the Kilogramme des Archives, highly polished reference prototypes manufactured from pure platinum and locked away in the French National Archives. The journey of the metric system was not without resistance. In 1812, Napoleon Bonaparte revoked the strict metric laws, issuing a hybrid system called the mesures usuelles that restored old customary names but redefined them as round multiples of the metric units. It was not until 1840, after the collapse of the Napoleonic Empire, that the pure metric system was forcefully reimposed in France, eventually spreading across Europe due to its undeniable scientific and commercial utility. By the latter half of the 19th century, global industrialization required unprecedented international coordination. On May 20, 1875, representatives from 17 nations gathered in Paris to sign the Metre Convention, one of the first truly modern international scientific treaties. This treaty established the enduring framework for global measurement. It created the International Bureau of Weights and Measures, known by its French acronym BIPM, to act as the central laboratory in Sèvres, France. It also established the International Committee for Weights and Measures, the CIPM, comprised of prominent metrologists to provide scientific direction, and the General Conference on Weights and Measures, the CGPM, to act as the ultimate plenary organ, where member nations vote on major metrological decisions. Under the Metre Convention, the era of artifact metrology was formalized. Scientists realized that the original pure platinum archives from 1799 were too soft for enduring centuries-long use. Consequently, new prototypes were cast from a specialized alloy consisting of 90% platinum and 10% iridium. This specific mixture greatly increased the hardness of the metal while retaining extreme density, low magnetic susceptibility, and an almost total resistance to oxidation. In 1889, the international prototype of the kilogram, affectionately nicknamed Le Grand K, and the International Prototype Meter were officially sanctioned to replace the old archives. Member nations were issued official sister copies of these artifacts, allowing local laboratories to trace their measurements back to the primary standards in France. However, this era was defined by a profound, inescapable vulnerability. By anchoring universal constants to physical objects, humanity had tied the fundamental laws of science to terrestrial artifacts subject to the relentless forces of entropy. If the international prototype of the kilogram were to be dropped, scratched, or destroyed, the mass of the entire world would, by definition, instantaneously change. An artifact is merely a piece of metal. It is not a law of physics. As the 20th century dawned and the demands of quantum mechanics and electromagnetism grew, the scientific community realized that this philosophical and practical vulnerability could no longer be ignored.
The period spanning from the 1960s to the early 1980s represented a monumental philosophical inversion in the science of measurement. For thousands of years, humans had defined units based on macroscopic, human-scale phenomena, the swing of a pendulum, the length of an arm, the rotation of the Earth, and then attempted to scale those measurements down to observe smaller things. The mid-20th century saw metrologists flip this hierarchy. Armed with the tools of atomic physics, scientists began to define base units using the infinitesimal subatomic behaviors of nature, scaling those precise quantum definitions up to measure the macroscopic world. This transformative era began with the formalization of the International System of Units, abbreviated universally as the SI. Adopted at the 11th General Conference on Weights and Measures in 1960, the SI was designed to be a coherent, evolving framework capable of supporting the most rigorous demands of modern science, electromagnetism, and industrial engineering. Most significantly, the year 1960 marked the metrologists' community's first definitive break from the physical artifacts that had governed the world since the 19th century. General Conference officially abandoned the 1889 platinum-iridium International Prototype Meter.
In its place, the meter was redefined based on the wavelength of radiation emitted in a vacuum by the krypton-86 atom when it transitioned between two specific energy levels. The exact definition set the meter equal to 1,650,763.73 wavelengths of this specific orange-red emission line. This was a watershed intellectual moment. Length was no longer a metal bar locked in a French vault. It was now an invariant property of atomic light, a standard that could be independently reproduced by any suitably equipped physics laboratory anywhere in the universe, without needing to compare it to a physical object. However, the most fundamental shift of this era occurred in the domain of timekeeping, forever altering humanity's relationship with the passage of time. Historically, the second had been an astronomical unit, derived as a specific fraction of the time it took the Earth to complete a single rotation on its axis. Yet, as scientific instruments grew increasingly sophisticated, it became glaringly apparent that the Earth is a remarkably poor timekeeper. Our planet's rotation fluctuates unpredictably due to the drag of ocean tides, shifting atmospheric weather patterns, and internal geological movements. A unit of measure meant to be universal cannot be anchored to a fluctuating planetary standard. Consequently, in 1967, the scientific community fundamentally redefined the second, moving away from the macroscopic rotation of the Earth and embracing the microscopic certainty of atomic time. The new definition was anchored to the Cesium-133 atom. According to the principles of quantum mechanics, atoms absorb and emit energy in very specific, discrete amounts, known as quanta. When a cesium atom transitions between two specific hyperfine energy levels in its ground state, it emits microwave radiation at a highly consistent resonance frequency. The second was officially redefined as the duration of exactly 9,192,631,770 periods of this specific radiation. This shift to the cesium standard elevated time to the status of the most precisely measurable quantity in existence. The reason for this unmatched precision lies in the nature of how frequency is measured. Unlike determining length or mass, which requires the continuous comparison of physical magnitudes, a process inherently fraught with minute observational errors, frequency can be measured simply by counting discrete events. Counting the individual ticks or wave periods of an atomic transition is an exact mathematical operation. By reducing timekeeping to the act of counting atomic oscillations, time measurements achieved degrees of certainty that were physically impossible for any other metrological quantity. The supreme, unquestionable precision of atomic timekeeping inevitably forced yet another metrological crisis, this time regarding the speed of light. Throughout the 1970s, physicists repeatedly measured the speed of light using the newly defined krypton-86 meter and the highly precise Cesium-133 second. The precision of modern lasers and atomic clocks advanced so rapidly that the limiting factor in measuring the speed of light was no longer the measurement instruments themselves, but the inherent uncertainty in the definition of the krypton meter. The physical inability to perfectly realize the exact wavelength of krypton radiation was restricting further scientific progress in electromagnetism and astronomy.
The solution, adopted at the 17th General Conference on Weights and Measures in 1983, was an act of profound theoretical elegance. Rather than attempting to find a sharper optical ruler to measure the speed of light, the international metrology community decided to fix the speed of light as an exact, immutable, universal constant. The speed of light in a vacuum, represented by the constant c, was defined as exactly 299,792,458 meters per second. Consequently, the definition of the meter was entirely rewritten. The meter was redefined as the length of the path traveled by light in a vacuum during a time interval of exactly 1/299,792,458 of a second. This 1983 redefinition fundamentally altered the underlying architecture of the International System of Units. By setting an exact numerical value for the absolute speed limit of the universe, length and time became permanently and inextricably linked. The meter was no longer an independent base quantity derived from the size of the Earth or the emission of an atom. It was now a derived manifestation of the atomic second and the speed of light. This conceptual leap proved that human measurement systems could successfully transcend the physical realm and anchor themselves strictly to the invariant rules that govern spacetime. Yet, even as the meter and the second embraced the physics of the cosmos, the global system of mass remained stubbornly anchored in the 19th century. As the 20th century drew to a close, a glaring, embarrassing inconsistency remained at the heart of the SI system. The kilogram was still just a piece of metal sitting in a vault. While the definitions of length and time had elegantly transcended their terrestrial origins by the late 20th century, the global system of mass was hurtling toward an existential and scientific crisis. The international prototype of the kilogram, the platinum-iridium cylinder forged in 1879, was failing its most fundamental duty, remaining constant. The era spanning the 1990s to the historic vote in 2018 represented a frantic, globally coordinated scientific endeavor to avert this crisis by completely rebuilding the foundations of metrology upon the bedrock of quantum mechanics. The artifact crisis was uncovered gradually during the rare, highly controlled periodic verifications of the national prototype kilograms. The BIPM maintained 6 official copies, referred to as witnesses, kept in the identical subterranean vault under the same triple-locked temperature-controlled conditions as Legrand K. When these witnesses were carefully extracted every few decades and compared against the primary prototype using incredibly sensitive mass comparators, scientists discovered a deeply disturbing trend. The masses of the cylinders were diverging. Over the course of a century, the official witness copies were observed to have drifted, becoming heavier relative to the international prototype by an average of 50 micrograms, roughly the mass of a small grain of sand or a human eyelash. This scientific conundrum presented deeply unsettling, bordering on the absurd. Because the international prototype was the absolute defining standard of mass, it could not, by definition, change its mass. It was always exactly 1 kilogram. Therefore, officially, the rest of the universe was changing around it. Physicists could not ascertain whether the central prototype was losing mass due to microscopic wear and tear, or if the witness copies were gaining mass due to the aggregation of airborne contaminants, carbon outgassing from the metal, or the accumulation of trace mercury vapors. To mitigate surface contamination, the BIPM instituted a rigorous, painstaking cleaning protocol. This involved wiping the cylinders with chamois leather soaked in ether and alcohol, followed by a meticulous steam cleaning process. This cleaning protocol was found to consistently remove roughly 15 to 16 micrograms of mass from the prototypes. The stark reality that the fundamental unit of mass fluctuated based on a laboratory washing schedule forced the international metrology community to recognize that artifact-based measurement was scientifically obsolete, unreliable, and intellectually indefensible. Furthermore, the instability of the kilogram was not isolated. It was actively infecting the rest of the measurement system. The definition of the ampere, the base unit of electrical current, was historically tied to the kilogram through the measurement of mechanical force. Consequently, the inherent uncertainty in the physical mass of the kilogram placed a hard, unbreakable limit on the accuracy of all global electrical and thermodynamic measurements. By 1990, the situation had become so untenable for modern engineering that electrical metrologists essentially rebelled against the official SI definitions. They formally broke away and adopted conventional, highly precise values for electrical units based entirely on quantum phenomena. These quantum electrical foundations relied on 2 critical discoveries. The first was the Josephson effect, which occurs when 2 superconducting materials are separated by a thin insulating barrier. When exposed to microwave radiation, this junction produces a voltage that is perfectly quantized, stepping up in exact increments related directly to the frequency of the microwaves and fundamental constants. This allowed for a perfect invariant definition of the volt. The second discovery was the quantum Hall effect, observed in 2-dimensional electron systems subjected to low temperatures and strong magnetic fields. This effect quantizes electrical resistance into exact, predictable steps, allowing for an invariant definition of the ohm.
While the adoption of these quantum electrical standards solved practical engineering problems, it created a fractured metrological system where the official SI units were completely misaligned with the highly precise quantum standards actually used in laboratories worldwide. To resolve this crisis and reunite the system of units, the kilogram had to be completely redefined using an invariant constant of nature. The target was the Planck constant, the fundamental value in quantum mechanics that describes the sizes of the quanta, linking energy, mass, and frequency. Achieving this required the most complex metrological experiments ever conceived, pursued relentlessly by national laboratories worldwide. Two primary experimental pathways were utilized to bridge the macroscopic world of human weights to the microscopic world of quantum mechanics. The first pathway was the Kibble balance, originally known as the Watt balance. This intricate electromechanical apparatus operates by balancing the downward mechanical force of a macroscopic mass in a gravitational field against an upward electromagnetic force generated by a coil of wire suspended in a magnetic field. By substituting traditional, error-prone macroscopic measurements of voltage and resistance with the perfect quantum measurements derived from the Josephson and quantum Hall effects, the Kibble balance allows a physical mass to be weighed directly against the Planck constant.
The second pathway was the International Avogadro Project, an endeavor of astonishing manufacturing precision. Scientists engineered nearly perfect spheres of a single, highly purified silicon isotope. These spheres were polished so smoothly that if one were scaled up to the size of the Earth, the distance between the highest mountain peak and the deepest ocean trench would be a mere few meters. By precisely measuring the volume of the perfect sphere and using X-ray crystallography to determine the exact spacing between individual silicon atoms in the crystal lattice, scientists could literally count the number of atoms contained within the sphere. This allowed for an unprecedented measurement of the Avogadro constant, providing an alternate, completely independent route to defining the kilogram by linking macroscopic mass directly to the mass of a single atom. For years, the results from the global array of Kibble balances and the silicon sphere experiments showed minute, frustrating discrepancies, forcing the international community to delay the redefinition. It was not until 2017 that the experimental data finally converged with sufficient robustness, achieving uncertainties of mere parts per billion. This finally satisfied the incredibly stringent criteria demanded by the Consultative Committee for Units. This unprecedented scientific consensus culminated at the 26th General Conference on Weights and Measures, held in Versailles in November 2018, in a historic emotional vote that effectively ended the artifact era forever. Representatives from 60 nations unanimously agreed to revise the International System of Units. Coming into force on May 20, 2019, the anniversary of the original Metre Convention, the redefinition completely decoupled the SI from any physical artifacts. The 2019 revision permanently locked the exact numerical values of four fundamental constants of nature. The Planck constant was fixed to exactly 6.6260715 times 10 to the power of negative 34 joule seconds, permanently defining the kilogram without a physical cylinder. The elementary charge of an electron was fixed to redefine the ampere, eliminating its reliance on mechanical force. The Boltzmann constant was fixed to redefine the Kelvin, shifting temperature measurement away from the physical triple point of water to a pure measure of fundamental thermal energy. Finally, the Avogadro constant was fixed to exactly 6.022140076 times 10 to the power of 23 elementary entities, redefining the mole. The mole was transitioned from a mass-dependent unit to a pure, exact number of atoms or molecules. The philosophical and practical impact of the 2019 redefinition cannot be overstated. By anchoring the base units directly to the fundamental fabric of reality, the metrology community finally fulfilled the utopian vision articulated during the French Revolution. The system was now truly, unassailably universal. Because the speed of light, the Planck constant, and the elementary charge are presumed to be invariant everywhere across the cosmos, The new SI system can be utilized not just by any laboratory on Earth, but theoretically by any advanced civilization anywhere in the universe. Condorcet's dream was finally realized. Humanity possessed a measurement system truly designed for all people, for all time. On a practical level, while the general public noticed no change when buying a kilogram of flour, this quantum foundation provided advanced pharmaceutical companies and high-tech semiconductor manufacturers with the infinite precision required to innovate at extreme microscopic scales.
Having successfully untethered measurement from the physical constraints of terrestrial artifacts, metrology is now undergoing a radical transformation driven by the extreme limits of quantum physics, the dawn of artificial intelligence, and the exploration of the wider cosmos. The horizon spanning the present day to the 2030s is characterized by pushing precision into realms where the fundamental forces of gravity and quantum mechanics intersect, and by fundamentally restructuring how measurement data interacts with the rapidly expanding digital world. The most imminent and profound shift on this horizon is the impending redefinition of the second. While the current cesium-based atomic clock has served as the unshakable bedrock of global timekeeping since 1967, it operates at microwave frequencies, oscillating roughly 9 billion times per second. However, a revolutionary new generation of timekeepers known as optical clocks has emerged. These clocks, utilizing elements like strontium, ytterbium, and highly trapped aluminum ions, operate at optical frequencies, using the visible light spectrum, which allows them to tick hundreds of trillions of times per second. These devices operate on the bleeding edge of quantum physics. Optical lattice clocks, for instance, trap thousands of ultra-cold atoms in a web of intersecting laser beams. They exploit a highly counterintuitive quantum phenomenon known as the magic wavelength, a specific frequency of light where the intense electromagnetic fields of the trapping lasers do not interfere or shift the delicate resonant frequencies of the trapped atoms. Single-ion clocks go even further, isolating a lone electrically charged atom in an electromagnetic trap, representing the ultimate isolation and control of a quantum system. These optical clocks have achieved proven accuracies on the order of 10 to the power of -18, a relative frequency precision that surpasses the best current cesium fountains by 2 full orders of magnitude. To conceptualize this staggering level of exactitude, if an optical clock had started ticking at the exact moment of the Big Bang, approximately 14 billion years ago, it would not have lost or gained a single second. This staggering precision has driven the Consultative Committee for Time and Frequency to formally initiate the long, complex journey toward redefining the SI second, a milestone highly anticipated to occur by 2030. The primary hurdle is no longer building the clocks themselves, but successfully comparing them. High-precision clock comparisons are currently limited to subterranean optical fiber networks spanning roughly 1,000 kilometers. To redefine a global unit of time and maintain coordinated universal time, intercontinental comparison is absolutely mandatory. Consequently, international collaborations are pioneering new independent radio techniques to bridge the continents. They are utilizing very long baseline interferometry, a technique originally used by astronomers to image distant galaxies and black holes, to connect optical clocks across oceans, using the highly energetic radio signals from distant extragalactic quasars as fixed celestial reference points. Simultaneously, they are deploying integer ambiguity precise point positioning techniques using advanced satellite navigation signals to constantly compare clocks worldwide. Simultaneously, the foundational infrastructure of metrology is undergoing a massive digital transformation to actively support the advent of Industry 4.0, the Internet of Things, and the integration of artificial intelligence in manufacturing. The transition from physical, paper-based calibration certificates to the digital SI framework represents a paradigm shift from human-readable documents to fully machine-actionable data. At the core of this transformation is the digital calibration certificate. Rather than a static PDF, the digital calibration certificate is an encrypted, smart XML data object based on an internationally agreed-upon schema. In modern, highly automated manufacturing environments, such as pharmaceutical production lines or semiconductor fabrication facilities, traditional paper calibration certificates introduce unacceptable vulnerabilities. They are prone to human transcription errors, introduce latency in data processing, and cannot be dynamically integrated into automated quality assurance systems. Digital calibration certificates eradicate these issues by allowing machines, databases, and sensors to autonomously interpret metrological data without human intervention. This seamless communication is facilitated by the DSI metadata model, an international standard that ensures complex measurement data, including the necessary timestamp, the specific SI unit, and the exact expanded measurement uncertainty, are universally understood by digital networks. This machine-to-machine metrological communication is the critical, foundational enabler for the widespread adoption of digital twins. Digital twins are dynamic, virtual replicas of physical assets, ranging from individual robotic arms to entire power plants that continuously update with real-time sensor data. If a digital twin is to accurately simulate the real world and reliably predict the maintenance needs of a jet engine or an industrial process, it must possess absolute, mathematically proven certainty regarding the calibration status and measurement uncertainty of every physical sensor feeding it data. The digital SI framework secures this chain of trust. By integrating cryptographic digital signatures directly into the machine-readable certificates, the system prevents tampering and ensures that AI algorithms do not hallucinate or make catastrophic operational decisions based on faulty, uncalibrated, or untraceable physical measurements. Finally, the relentless, centuries-long pursuit of measurement precision has elevated metrology beyond the factory floor, transforming it into the primary instrument for probing the deepest mysteries of the universe, particularly the rigorous testing of Albert Einstein's theory of general relativity. Relativistic metrology leverages the extreme sensitivity of modern instruments to physically observe the subtle, continuous warping of spacetime. This is most spectacularly demonstrated by the Laser Interferometer Gravitational Wave Observatory. To successfully detect the gravitational waves originating from the violent collisions of massive black holes billions of light-years away, the observatory must measure changes in the length of its 4 perpendicular arms to a precision roughly 1/10,000th the diameter of a single proton. Achieving this requires optical metrology bordering on the miraculous. The observatory's test masses, 40-kilogram mirrors forged from ultra-pure fused silica, are polished to atomic smoothness and coated in dozens of specialized layers. These mirrors are so perfectly crafted that they absorb only 1 out of every 3.3 million photons of infrared laser light that strike them, preventing thermal expansion from destroying the measurement. These mirrors are suspended in incredibly complex multi-stage passive and active vibration isolation systems to decouple them entirely from the terrestrial noise of earthquakes, weather, and traffic. To ensure the observatory acts as an accurate ruler for space-time, the National Institute of Standards and Technology provides highly specialized photon calibrators. These devices utilize the tiny, almost imperceptible radiation pressure of auxiliary lasers to physically push on the massive mirrors, simulating the exact effect of a gravitational wave to ensure the absolute accuracy of the primary detectors. The unparalleled success of this terrestrial metrology is now directly informing the development of the Laser Interferometer Space Antenna, a joint European Space Agency and NASA mission designed to create a massive gravitational wave detector in deep space, utilizing laser arms spanning millions of kilometers. Closer to home, the 18-decimal place precision of optical clocks has birthed an entirely new scientific discipline of relativistic geodesy. Albert Einstein's theory of general relativity dictates that gravity fundamentally warps the flow of time. A clock situated deeper in a gravity well will tick noticeably slower than a clock positioned at a higher elevation. Modern optical clocks are now so hypersensitive that they can detect the minute time dilation caused by a difference in elevation of a single millimeter. This allows metrologists to map the Earth's gravitational potential and determine height differences over vast distances, not by surveying physical space with lasers or leveling rods, but by measuring the chronometric differences between distant atomic clocks. In collaborative experiments between the National Institute of Standards and Technology and the National Oceanic and Atmospheric Administration, researchers transport portable optical clocks into the high elevations of the Rocky Mountains, measuring altitude by precisely calculating how fast time passes at the summit compared to the laboratory below. This capability represents the ultimate, profound synthesis of metrology and fundamental physics. The measurement tools developed by humanity have become so incredibly refined that the static Newtonian assumptions of absolute space and time are no longer sufficient to even operate them. In the 21st century, metrology does not merely measure objects residing within the physical world, it actively interrogates the relativistic, shifting fabric of reality itself. From the chaotic, subjective local markets of pre-revolutionary France to the precise observation of merging black holes across the cosmic void, the history of measurement is the ultimate narrative of humanity's ever-expanding intellectual capacity to understand, quantify, and master the universe.